Hello, welcome to my channel. Welcome to Rehandran. In this video of circuit response, time and frequency domain analysis, I'm gonna talk about RC sinusoidal response. So, what will the behavior of in series RC circuit be when the input is of sinusoidal nature? So, let's get started. In the previous circuit response video, I talked about RL sinusoidal response, and we got our time and frequency domain analysis results from which we deducted our RL response. So what will the behavior of the RC circuit be? So let us draw the circuit. Okay, so this is the RC circuit. So R and C, say RC circuit has initial voltage VO at V0 plus V0 minus, and the input is Vs sine omega t. Okay, so we are gonna analyze this circuit and we are gonna find the behavior, or we're gonna find the response of this series RC circuit. So in time domain analysis TDA, let us find the equation first. So RC circuit is an LTI system which abides by superposition principle. Thus we can apply KVL KCL. So let me apply KVL. So by KVL it will generate linear differential equation with constant coefficient, so in time domain obviously. So the for loop current, so R I plus 1 by C I t dt equals to these two voltages equals to the given input voltage. So the input voltage is Vs sine omega t. Now R plus, let me replace this integration by linear differential equation with constant coefficient. So 1 by c d, integration means 1 by d if differentiation is d. So I t equals Vs sine omega t. Now we have got for loop current, but the response of this RC circuit is voltage across capacitors. We know that current through the capacitor is it equals C d by dt V. So we are gonna plug this value. So R plus 1 by C d C. So let us substitute for different linear differential operator d and Vt, which will give Vs sine omega t. So this gives us RCD plus 1 VT equals Vs sine omega t. So our differential equation for the RC circuit in time domain for sinusoidal response is RCD plus 1 Vt equals Vs, which is the magnitude basically, and sine omega t. Now we are gonna analyze this. So we're gonna find out the complementary solution. So the complementary solution can be found by solving the characteristic equation of the LTI system. So RCD plus 1 equals 0. This is the characteristic equation. This equation is also the what we say complementary equation, okay, which will give us the complementary solution from which we can get the transient part of the response. So D is minus 1 by RC. So now we get the thus transient response. So transient response for any type of linear system, all we have to do is solve its complementary equation. So the complementary solution is the transient response of any linear system, okay, be it electrical or mechanical or anything. So response VTR in time domain, it's C1, which is the arbitrary constant e to the power minus t by RC. This is the transient response. Now for the particular integral. So for particular integral, which will give us the steady state response of the system. So particular integral Vt equals Vs sine omega t by RCD plus 1. Okay, now what to do? So we can break sine into complex exponential terms, okay, the sine term. So what we're gonna do is, okay, so it will be like this: V is e to the power minus e to the power j omega t minus e to the power minus j omega t by 2j d plus 1 by RC. Now all we can do is V is by 2j RC. So e to the power j omega t by d plus 1 by rc minus e to the power minus j omega t by d plus 1 by rc. This will give, so if we apply formula for uh, particular solutions, so for exponential um, parts, uh, the formula is like this. So so j omega t, this j omega will replace d, so j omega plus 1 by rc minus e to the power minus j omega t by minus j omega plus 1 by rc. This is the case. So now v is by 2j rc. Let me common out 1 by rc, which will give 1 by rc to the power j omega t plus 1 plus j omega rc minus either minus j omega t by 1 minus j omega rc. Now all we are gonna have to do is v is by 2j rc will cut out, so there is no component here. Now we are gonna get this j omega part here, so e to the power j omega t by r plus 1 by j omega c is to the minus j omega t by r minus r plus 1 by j omega c, and the common part is j omega c. So the common part is 1 by sorry, only j omega c is the common part from this. So now what we're gonna do is, so vs 2j j omega c, for now I'm saving this. So now it will give us e to the power j omega t by r minus j 1 by omega c minus, okay, let me common out the minus, so plus, it will be plus and e to the power minus j omega t by r plus j 1 by omega c. Now this has come to this, so let us assume something. So here say impedance of the RC circuit is r minus j 1 by omega c, which will be the magnitude, for which magnitude will be root over r plus 1 by omega c r square plus 1 by omega c square. and phi will be minus tan inverse 1 by omega c by r, which is minus tan inverse 1 by omega rc. So the impedance diagram will give us this. This is r, this is 1 by omega c, and this is phi. So j minus j, this is z, this is phi. So now we have got ourselves some made up terms. We will use it to solve this equation. So leave this. So this 2j if multiplied will become minus 2 omega c e to the power j omega t by z magnitude e to the power, this is Euler's form, j phi, and plus e to the power minus j omega t by z magnitude minus j phi. This is this, which will give us the value vs minus, so if we common out the term omega c z magnitude, and if we take the 2 inside, I have made some mistake. So here this will be j e to the power j minus omega minus j phi, minus j phi, and this will be plus. So we have to do is this. So plus e to the power minus j omega t plus phi by 2 minus vs by omega c z prime. This will if you see that e to the power j omega t plus phi plus e to the power minus j omega t plus phi by 2, this is obviously cos. So cos omega t plus phi, this gives us cos omega t plus phi. If we further break it down and rearrange this, it will give us the value. So if we say that 1 by omega c, 1 by omega c is z prime sine phi, so this will definitely give us minus vs z sine phi by z cos omega t plus phi. So we get minus vs, which is the magnitude, and z cuts out, sine phi cos omega t plus phi. So this is the particular integral of the uh, differential equation for RC series RC circuit. Now, so now we get the full response of the circuit in time domain. So now the complete response. So complete response of the circuit is Vt equals V transient plus V steady state, which is the complementary solution plus Pi particular integral. So we found that the transient response is C1 e to the power minus t by RC plus particular integral is this is this is minus, so minus Vs sin phi cos omega t plus phi. Now we have to find the arbitrary constant. So for arbitrary constant, we know that at V t equals 0, initial voltage across the capacitor is Vo equals C1 e to the power 0 minus Vs sin phi cos phi. So C1 is Vo minus Vs sin phi cos phi, which gives the solution. Thus Vt is Vo, this is plus Vo plus Vs sin phi cos phi e to the power minus t by RC plus, this is not plus, this is minus V S sin phi cos omega t plus phi. So this is the complete response of the RC series RC circuit to sinusoidal input in time domain. This is the response. Vt equals Vo, the initial voltage, plus Vs, the input magnitude, plus sin phi cos phi e to the power minus t by RC minus Vs sin phi cos omega t plus phi. I don't know, this is quite different from the value of RL response. RL circuit and RC circuit are quite similar. They are analogous, or they are kind of dual circuits. So it shouldn't be where for RC circuit the response is voltage, for RL circuit it is the current. So I don't know, you can check it for yourselves, but I don't think I made any mistakes. So let's see what the response of the RC circuit is in frequency domain. Okay, so here the input is Vs sin omega t, this is R and this is C, and we have initial voltage. So in frequency domain analysis, what we're gonna do is we are gonna use the apply the Laplace transform. So if we apply the Laplace transform, this LTI system will be transformed into this. So R is frequency independent, it will be unaffected, C will be converted, and the initial voltage, we will use the current source analogy to uh, describe the initial voltage in frequency domain. So this is CVO. The capacitor will transform into the reactance, or the reactance 1 by C. This is R, and this is Vs omega by AC square plus omega square. Now say this is node A, so we are gonna use KCL. So we are gonna analyze this circuit in frequency domain. Say we apply KCL for convenience, obviously, at node A. So we have chosen the reference directions. Now IR for branch R plus CVO. CVO is towards node A and IR is towards node A, equals to IC, which is from away from node A. V is omega by AC square plus omega square minus V S by R plus CVO equals, so this is the ground, equals C, sorry, S C V S, because we know that I equals V by X, which is V by 1 by C equals SCV. So, and may make it common. So is C R V S my V S plus V S equals V S omega by AC square plus omega square plus RC V O. Now is RC plus 1 V S equals Vs omega AC square plus omega square plus C VO. Okay, okay. So Vs is equal to Vs omega plus. So if we take this term and we divide it with these terms, it will give us like, so okay, v is omega s square plus omega square 1 plus is rc plus rc vo by 1 plus is rc. Now what we're gonna do is we're gonna break this. Okay, we're gonna partial fraction this term. So now, so say the partial fraction is a by src plus 1 plus bs plus c s square plus omega square plus rc vo by src plus 1. So if we see, um, 1 by c square plus omega square is rc plus 1 equals a by src plus 1 plus bs plus c by s square plus omega square. Let us multiply this term with the both the terms, so this will give 1, this a into s square plus omega square plus bs plus c is rc plus 1. Now let s equals minus 1 by rc, which will give us, this will be 0 and a will be 1 by r square plus c, not plus, it's r square c square. So r square c square plus omega square equals 1, which will give a equals r square c square by 1 plus omega square r square c square. Now let us write this here. A equals r square c square by 1 plus omega square r square c square. Now let us equate the coefficients of s square and s. We can also use the constant terms also. So coefficient, equating coefficient of s square and s. So if we equate the coefficients of s square and s, which will give us b rc plus a equals 0, which will give b equals minus rc by 1 plus omega square r square c square. So b is minus rc 1 plus omega square r square c square. Now let us equate coefficient of s. So b, here b plus c rc equals 0, which will give us c equals minus rc by 1 plus omega squared r square c square cross 1 by rc. So this will cut out, so which will give 1 by 1 plus omega square r square c square. So c is 1 by 1 plus omega square r square c square. We can also equate the coefficients. So sorry, we can also equate the constant terms. So a omega square plus c equals 1, which will give us c equals 1 minus a omega square. So 1 plus omega square r square c square minus r square c square omega square by 1 plus omega square r square c square. So this cuts out, which gives 1 plus omega square r square c square, 1 by 1 plus omega square r square c square, which is the same for c. Now let's plug this value and see what happens. So what we are gonna do is v is omega r square c square by 1 plus omega squared r square c square is plus 1 by rc plus minus rc is plus 1 by 1 plus omega squared r square c square s square plus omega square. Now what we're gonna do is take the common term out. So in both the, okay, we have forgot the, see here, say vo is s plus 1 by rc. So if we take the common rc out, it will cut out the this term rc on the numerator. So the result will be this. So now let us take the common out. V is omega by 1 plus omega square r square c square, and this is rc by s plus 1 by rc minus rc is by s square plus omega square plus 1 by s square plus omega square plus vo by s plus 1 by rc. Now let us take this omega and bring this inside the brackets. What will happen is, so v is by 1 plus omega square r square c square. This will give omega rc by s plus 1 by rc minus omega rc is by s square plus omega square plus omega by s square plus omega square plus VO by S plus 1 by RC. Now, what shall we do? Let us define some terms. Let us define the impedance of the RC circuit and phase and as we have done in time domain analysis. We will do this also here. So say Z impedance is R minus J1 by omega C, and phi is minus tan inverse 1 by omega RC. So if we draw this, so this is J, this is the Z, where this is R and this is 1 by omega C, and this is phi. So phi when taken anti-clockwise is positive, and when taken clockwise the angle phi is considered negative. This is convention. This is minus J, and this is real axis. The vertical is the imaginary axis. Now what we're gonna do, so we can say that one, so here there's no, okay, so R is Z magnitude cos phi, and 1 by omega C is Z magnitude sin phi. We're gonna use these facts, and Z is, and also Z magnitude is root over R square plus 1 by omega C whole by omega C Z. This is square because this will be squared. Okay, so here Z square is omega square C square 1 plus omega square R square C square. Now let us rearrange this. So if we take common omega C out of the bracket, it will give us, so 1 by omega C, this is R 1 by S plus 1 by RC minus R S by S square plus omega square plus 1 by omega C omega by S square plus omega square plus VO by S plus 1 by RC. Now what are we gonna do is uh, cut this out. So Vs by omega, okay, I have made some mistakes. Okay, so here, so Z is 1 by omega C omega square R square C square plus 1. Okay, so Z square is 1 by omega square C square 1 plus omega square R square C square. This is the right derivation. So here and here omega c commoned out is omega square c square. Now this is the right arrangement. Now if we cut out this, it will leave us with omega c z square r. So if we use inverse Laplace transform now, so it will give us e to the power minus t by rc minus r. This is cos omega t plus 1 by omega c sin omega t plus vo e to the power minus t by rc. So vs by omega c z square. So r is z cos, say r is z magnitude cos phi, and e to the power minus t by rc minus z cos phi cos omega t plus this is sin omega, sorry, sin phi sin omega t plus vo e to the power minus t by rc. Vs by omega c z square, we have common out z, the magnitude part, leaving us with e to the power minus t by rc cos phi minus, say let us make this common, take the minus out, so cos omega t cos phi minus sin omega t sin phi plus vo to the power minus t by rc. So now we'll cut this out. So vs by omega c z magnet impedance, magnitude of it, and minus t by rc minus this, by trigonometric identity it will be cos omega t plus phi. Here cos phi plus vo e to the power minus t by rc. So if we further rearrange this, so say we want to do something about this omega c and z magnitude, so say v is 1 by omega c is z sin phi and z magnitude, and this term minus t by rc minus cos phi minus cos omega t plus phi plus vo e to the power minus t by rc. So these terms will cut out, leaving the these terms, and it will give us um, v s cos, okay, say vo plus vs sin phi cos phi e to the power minus t by rc minus vs sin phi cos omega t plus phi equals to, okay, let me write this thoroughly, inverse Laplace transform of vs. Vs is at node A, so which is in time domain vt. So this is the answer for RC response in frequency domain. So there's an extra term sin phi in both time domain analysis and in this frequency domain analysis. We have got this extra term. We didn't get this extra terms in RL sinusoidal response, but in RC sinusoidal response we're getting an extra sin phi term. If this extra term wasn't here, then I think it will be the same perfect answer as we got in RL sinusoidal response. So do discuss it uh, among yourselves and with your professors, teachers. And now in summary, in both series RC response to sinusoidal input in both time domain and frequency domain analysis is of the value Vt, which is voltage across the capacitor, is Vo, which is the initial value plus the final magnitude of the sinusoidal input into sin phi cos phi e to the power minus t by rc. This full term is the transient response or the complementary solution minus vs sin phi cos omega t plus phi. This is the steady state response. This is transient response and this is steady state response. Thus this is the answer to the sinusoidal response of series RC circuit. So that's it for today. We have all thus far discussed um, source free RLRC response, step response of RLRC circuit, and now with this we have finished the sinusoidal response of series RL and RC circuit. If you have any doubt or any problem in understanding my explanation, you can uh, reach me. You can text in the comment section, and if you like my video, like and subscribe and share my video, and thank you.